In this video, we're going to talk about enthalpy changes and Hess's law. The learning outcomes you should take away from this video are to understand that reactions can be exothermic or endothermic, should be able to construct enthalpy profile diagrams for reactions, explain and use the terms standard conditions, enthalpy change of reaction, formation and combustion. You should also be able to calculate enthalpy changes using the formula Q equals mc delta T and use Hess's law to construct enthalpy cycles. You should also be able to determine enthalpy changes from enthalpy cycles. So what is enthalpy? Enthalpy, the symbol for which is H, is the heat energy stored in a chemical system. We can't measure the absolute value of this experimentally, so what we're interested in is the enthalpy change, delta H, in a reaction. This is the energy exchanged with the surroundings at constant pressure. The first law of thermodynamics says that energy may be exchanged between a system and the surroundings, but the total energy remains constant. So here we just underline some key concepts. The enthalpy is the heat energy stored in a chemical system, the enthalpy change is the heat exchange with the surroundings at constant pressure, and the first law of thermodynamics says that the total energy remains constant. One type of reaction which you should already be familiar with are exothermic reactions. In an exothermic reaction, heat energy is released to the surroundings. This causes an increase in temperature. If we look at the reaction profile, which shows the enthalpy of the system at different points throughout a reaction, we see that the reactants start off with a high enthalpy and then give out heat energy to the environment. This means that the products have less enthalpy than the reactants, and therefore overall in the reaction, the enthalpy change is negative. We also have endothermic reactions. These are reactions where heat energy is taken in from the surroundings. This means that the temperature decreases. These are the reactions that feel cold if you hold the test tube in your hand. If we look at the reaction profile again, the reactants start out with a low enthalpy and then they take in heat energy from the surroundings, so finish up with a higher enthalpy. This is why the overall enthalpy change in the reaction for endothermic reactions is positive. Thermodynamics is a subject rooted in experiment. You will find yourself working with data books which record the enthalpy changes for many different reactions. These reactions are always carried out under standard conditions, and you must know what these conditions are. The conditions are a pressure of 100 kilopascals, a temperature which is stated and is usually 298 Kelvin or 25 degrees Celsius, and a concentration of 1 mole per decimeter cubed if they're dissolved in water. The standard state of a substance is its physical state under standard conditions, so that is whether it is a solid, liquid or gas under the conditions listed above. The first standard enthalpy change you'll find yourself using a lot is the standard enthalpy change of reaction. This is the enthalpy change for a reaction which takes place with the molar quantities listed in the chemical equation. As always, it takes place under standard conditions and with all of the reactants and products in their standard states. The standard enthalpy change of reaction only has meaning with respect to an equation. As you can see below, the same reaction is taking place, but because the equation has been doubled, the enthalpy change must also double. The next enthalpy change we'll look at is the standard enthalpy change of combustion. This is the enthalpy change that takes place when 1 mole of substance reacts completely with oxygen under standard conditions and with all reactants and products in their standard states, as usual. This is an idealized reaction where only carbon dioxide and water are produced. In reality, quite often carbon monoxide is produced and the enthalpy change is slightly different. The final standard enthalpy change we'll look at for today is the standard enthalpy change of formation. This is the enthalpy change that takes place when 1 mole of a product is formed in its standard state under standard conditions from its constituent elements, which are also in their standard states. By definition, the standard enthalpy change of formation of an element in its standard state is 0, as it's already in the required form and takes no energy to get there. It's now time to talk about how to calculate enthalpy changes from experimental data. And firstly, we must know how to calculate how much heat energy has been transferred when something changes temperature. The formula shown here is how to do it. The heat transferred, Q, which is given in joules, is equal to the mass in kilograms times by the specific heat capacity, which has units of joules per kilogram per Kelvin, times by the change in temperature, which is given either in Kelvin or in degrees Celsius. Because it's a relative change and the increments are the same, it doesn't matter which you use. You use this formula to calculate the heat energy transferred to or from the surroundings, knowing that this will either have come from or gone into the chemical reaction. We'll go through how to do these calculations in more detail during the exam question at the end of the video. Some reactions are much easier than others to carry out. Hess's law gives us a way of carrying out the easy reactions and using them to calculate the enthalpy change for a reaction we're interested in. It states that if a reaction can take place by more than one route, where the initial and final conditions are the same, then the total enthalpy change is the same for each route. Consider the enthalpy profile shown below. There are two different ways to get from the reactants to the products. We can either go via the intermediates on the path shown in red, and we'll label the enthalpy changes on this three-stepped path, A, B, and C. Or we can go straight from the reactants to the products. We'll label this on the blue path an enthalpy change of D. Hess's law states that A, B, and C added together are equal to D. We can use Hess cycles to calculate enthalpy changes we're interested in. Consider wanting to know the enthalpy change of formation of methane. There are two paths from the constituent elements to the combustion products. The path shown in red, which consists of the formation of methane followed by combustion, the combustion has an enthalpy change of A, or the path shown in blue, immediate combustion of the elements with an enthalpy change of B. Hess's law says that the total enthalpy change of each path is the same. We can write this mathematically as delta H plus A is equal to B. We can rearrange this to give us the enthalpy change of formation as the enthalpy change of combustion of the reactants, B, minus the enthalpy change of combustion of methane, A. We can carry out a very similar process using the standard enthalpy changes of formation. Consider here wanting to know the enthalpy change of combustion of ethane. We can consider two paths from the constituent elements to carbon dioxide and water. We can use the green path, which consists of the formation of the reactants, having an enthalpy change of A, followed by the combustion of those reactants. Or we can directly form carbon dioxide and water from the constituent elements. This path is shown here in red. Hess's law says that the total enthalpy change of these two paths will be the same. So we can write delta H plus A is equal to B. Rearranging this gives us that the enthalpy change we're interested in, delta H, is the enthalpy change of formation of the products, B, minus the enthalpy change of formation of the reactants, A. We're now going to attempt the OCR Chemistry A AS paper, Chains, Energy and Resources, question 6. So before you attempt any question, it's always important to go through and highlight the key information to make sure you don't miss any of it. So that's what I'm going to do for you here. The first thing to notice about this question is the chemical formula they give you, because we're going to have to work with that. Then it draws your attention to the fact that this is an experiment about the enthalpy change of combustion. After that, it lets you know how much mass of alcohol is burned during the experiment, and also the mass of the water which is heated up. It then tells you the temperature change of the water and the specific heat capacity of the water. It wants you to calculate in moles the amount of alcohol that's burnt, and then calculate the enthalpy change of the combustion of the alcohol in kilojoules per mole. It tells you to give your answer to 3 significant figures. So I'm now going to go through the working. Firstly, it wants you to calculate the amount of moles of alcohol that burn. So we're going to use the chemical formula given here. We've got 5 lots of carbon at 12 grams per mole, 12 lots of hydrogen at 1 gram per mole, and 1 lot of oxygen at 16 grams per mole. That makes 88 grams per mole total. 1.54 grams of the alcohol was burnt, so if we divide that by 88 grams per mole, that gives us 0.0175 moles burnt total. Now we're going to use Q equals mc delta T to calculate the heat absorbed by the surroundings. The change in temperature is given here by 75.3 minus 22.8, 52.5 degrees Celsius change. The mass of water is 180 grams, the specific heat capacity is 4.18, and the change in temperature is 52.5. This gives us the total energy absorbed by the surroundings as 39,501 joules, so we know the chemicals gave out 39.501 kilojoules. If we divide this by the amount of moles we calculated earlier, we get the final answer of the enthalpy change of combustion of minus 2,257.2 kilojoules per mole. Remember to round your answer to 3 significant figures as you were asked in the question. That's it for today, guys, and all that's left to say at the end of this video is I hope you found it useful and thank you so much for watching.